Okay, so the last talk was a basic. The last talk was a basic overview. This talk will be somewhat at a research level, somewhat at a forefront research level, and you will see why it is so. However, I'll try to keep it as pedagogical as possible. If you want to stop me, then please do stop me and ask questions. The aim here is not to showcase everything, but to make sure that you understand at least some of the important concepts. Okay, so in this talk also we will need some of the concepts which we talked about in the last lecture. I think the most important concepts that we need to remember are what I already wrote down on the blackboard and circled: the frequency scales as 1 over mass, that the masses are redshifted due to cosmology, and the masses are redshifted to, since frequencies are redshifted to lower frequencies, masses are redshifted to higher masses. There was some confusion. The Z is not a power, the Z is a superscript, just because I had already 1 and 2 and C in the subscript. I didn't want to put in another subscript. The Z as a superscript just means that I multiply the quantity by 1 plus Z. I would say I'm just redshifting the quantity. It means I'm talking about the detector frame mass as opposed to the source frame mass. And I think these are the two of the most important things to remember. The third important thing that we will need is the fact that we are sensitive to phase as well as the amplitude. That is going to come back again in a few slides. So the plan of this part of the talk is I'm going to talk about LIGO, Virgo, Kagra observations in general, which I didn't go over in the last talk. And I'm going to talk about some of the key science highlights from LIGO, Virgo, and Kagra. Then most of the talk is going to be on what we call standard siren cosmology. I'm going to tell you what standard sirens are, and we are going to talk about bright and dark standard sirens, some of the current results, and some of the current challenges, some of the future prospects. And then end by very briefly mentioning some other aspects of cosmology other than standard sirens, which I don't cover in this lecture. Hopefully by the end of this lecture you will appreciate why gravitational waves has to be a module in a school or in a course on cosmology now. But let's step aside for a bit. Let's talk quickly about the LIGO, Virgo, and Kagra observations. We already mentioned the observation of the binary black hole merger, GW 150914, our first discovery, and it of course shook the major news headlines all over the globe, and it not only made it to the news headlines but also to popular media. Here you see a cartoon from the New Yorker where two birds are saying, was that you heard just now, or was it two black holes colliding? It's a pun on the chirp signal which we mentioned in the previous lecture. So just GW 150914 was the first direct detection of gravitational waves. It was the first direct observation of a black hole. It's a direct observation because here the signal is coming directly from the black hole as opposed to from around the black hole. It was a discovery of heavy black holes of masses greater than 30 solar masses. It was a 30-40 solar mass system. Before GW 150914, many people didn't even believe that black holes 30-40 solar masses could exist. I mean, most astrophysical mechanisms, they tend to prefer much lighter black holes. It was the first observation of a black hole in a binary. We had observed neutron stars in binaries, but not black holes. And the two black holes merged and formed a third black hole. So it was the first observation of a black hole forming. When you form a black hole, then you essentially end up with a perturbed black hole which has certain signatures, it's ring down modes, you exactly see stuff coming out of the horizon that tells you a lot about the strong field regime of gravity. Of course, this was the first discovery paper. After that, there were a number of other papers on binary black holes until finally the binary neutron star, GW170817, was observed.
So, yeah. Because here it's only on one slide, so it's saying that your screen sharing is paused. So it's the recording. So screen sharing.
I need to go there and
resume share on top. Yes. And yeah, so now we can.
Okay, so the GW170817, it was a binary neutron star. I said that the binary black hole was a 30-40 solar mass black hole. The neutron star is, what kind of masses are we talking about now? Somebody? About 1.72-ish solar masses, 1.7 solar masses. So the mass is much, much lower, more than 10 times lower. If the mass is lower, what should we expect? Smaller amplitude. Smaller amplitude, what else should we expect?
Higher frequency.
Higher frequency. If the mass is smaller, then we expect a higher frequency. Higher frequency means, essentially most of the time we have our band, we are not sensitive to frequencies below 10 hertz or 20 hertz. In this case, we are not sensitive to frequencies below to 20 hertz. So higher frequency just means that the signal spends a very long time in the band and then merges at high frequencies. Because it spends a long time in the band, you see a much longer in spiral here than you had seen for the binary black hole. And you can see that it's the binary black hole signal kind of ended at 200, 250 hertz. Here it goes on up to 300, 400, 1000 its hertz. We actually do not know what happens really at high frequencies. So once again, telling us that we are observing a low mass system potentially coming from neutron star mergers. But what happened 2 seconds after that really told us that we are observing neutron star mergers, because about 1.7 seconds after the gravitational wave chirp ended, we observed a gamma ray burst, which essentially came from the material that the neutron star is composed of. Also has all kinds of other interactions, including strong and electromagnetic interactions. So when there's a merger involving a neutron star, you expect not only gravitational radiation, but also a bright electromagnetic radiation, potentially also neutrinos, which we unfortunately did not observe conclusively. So the first electromagnetic signal came as a gamma ray burst about 1.7 seconds after the merger. Then all astronomers, they pointed their telescopes in the region of the sky. It was almost every telescope that could observe was pointing in this particular spot in Hydra in the sky, and about 10 hours later, the optical counterpart was discovered. The optical counterpart slowly faded away from optical to near infrared, far infrared, and eventually gave out radio afterglows. So it was observed in several bands in electromagnetic astronomy. This even gave birth to multi-messenger science with gravitational electromagnetic waves. They confirmed that binary neutron star coalescences are progenitors of short gamma ray bursts. We did not, it was only an idea that these binary neutron star coalescences could be progenitors of such short GRBs. In the kilonova, we could see these spectral lines from heavy elements. So it demonstrated these mergers as the sites of heavy element formation. This really explains the abundance of heavy elements now, which could not have formed in other astrophysical processes. The fact that the gamma ray bursts, the signal from the GRB and the gravitational wave, they arrived almost at the same time after traveling for millions of years. Constrained the speed of light with respect to speed of constrain the speed of gravity with respect to light. We know that the gravity is now is traveling exactly at the speed of light. This actually killed a number of modified gravity theories which would have propagated different speed of gravity than it is from the speed of light. The neutron star equation of state is not very well measured in other ways, not very well calculated, even with QCD, perturbative QCD, lattice QCD. So it gave us access to the elusive neutron star equation of state. It told us about how neutron stars deform in the presence of gravitational field. And finally, it provided a novel measurement of the Hubble constant, which is something that is going to be the topic of this lecture. This was towards the end of the second observing run of LIGO and Virgo in 2017. As of now, we have had three observing runs. The third observing run was until the end of 2020. It unfortunately was brought to a close when COVID struck. It would have gone on for a month or two after that maybe, but the instruments were due for an upgrade. The instruments are still undergoing upgrade, and we expect a fourth observing run to start sometime early to mid next year. This was a quick introduction to all the gravitational wave, gravitational wave observations from LIGO, Virgo, and Kagra. Just a recap here, we see all the observations put together in a periodic table. There are of the order of 90 observations. We see black holes. So we see progenitor black holes as heavy as 95 solar masses or so. We see remnant black holes as heavy as 175 solar masses. We see some asymmetric systems. We see some neutron stars which have a slightly different color over here. I think it's GW170817. There are some other neutron stars. There are some neutron star black hole mergers. These were observed in January 2020. Soon after each other, there should be another neutron star hiding somewhere, but essentially this is what our list of detections looks like. So the topic standard siren cosmology, I'm going to explain why we call them standard sirens. We already heard about standard candles yesterday from Maciek, and so the gravitational waves are standard sirens essentially, again, because we are sensitive to both the amplitude and the phase. Because we are sensitive to phase, we can already obtain some estimate of the redshifted chirp mass. This is not a power, this is a superscript, which is just the chirp mass times 1 plus z. The phase evolution just tells us the redshifted chirp mass. I wrote down some complicated expressions in the previous lecture. The rest of the complicated expressions are not very important, but you should remember that the amplitude itself scales as this chirp mass, redshifted chirp mass over distance times some function of the angles. So if one measures the chirp mass from the phase and plugs it back into the amplitude, then one knows what the distance is. If one puts in some distance, then one can compute what amplitude to expect. If one observes a higher amplitude, then one knows that the source must be a bit closer. Good. The only caveat here is there is also this multiplication by some function of angles, which could be a slightly complicated function essentially of the inclination. And I mentioned earlier that we are not very sensitive to inclination. We measure it to some extent, but not very well. So this induces some kind of a degeneracy between distance and inclination, which I'm also going to come again in a few slides. However, the summary is they give us a direct access to the luminosity distance. And remember from yesterday how other measures of luminosity distance, they rely on various steps of calibration, how you need various rounds of the distance ladder starting from parallax. Here, instead of using any kind of distance ladder, you get the distance directly, which is kind of fantastic. And because of this, they are standard distance indicators, and they are called standard sirens. The analogy that gravitation wave is like sound as opposed to light is already there, so instead of standard candles, we call these sources standard sirens. So what can we do with standard sirens? What could we do with standard candles? With standard candles, we could measure the cosmological parameter, including the Hubble parameter, the local expansion rate of the universe. I think this slide is very too childish for this kind of an audience. Correct me if I'm wrong. Essentially, to measure the distance along with the distance and some other quantity, one can measure the Hubble constant. What other quantity? What is the other quantity that we need? The distance and velocity, recession velocity, which is essentially redshift, because the recession is due to cosmological redshift. So one needs distance and the redshift. Once again, let's consider this a recap. This is the first diagram from Hubble of the measurement of the Hubble constant, where Hubble forgot the per second on the vertical axis. This velocity should be measured in kilometers per second and not in kilometers, and obtained a Hubble constant of about 700 kilometers per second, about 1,000 kilometers per second per megaparsec. No, sorry, it's about 500 kilometers per second per megaparsec. How much is it now? It's about 7 times bigger than the quantity we know now, 70 kilometers per second per megaparsec. This only illustrates how difficult a measurement this is, the measurement of the Hubble constant. We can skip the next two slides, since these were covered yesterday. The measurement of the Hubble constant can come from local measurements, or it can come from the very early universe, where you use the CMB fluctuations, and with the CMB fluctuations you measure the Hubble constant back in the very early universe. With a cosmological model, you can extrapolate it to the Hubble constant in the present epoch. We know that the measurements of the Hubble constant from using supernovae and using CMB, they differ. The supernovae measurement, they give a slightly higher value, such as 74 kilometers per second per megaparsec. The CMB measurements give a slightly lower value, such as 64 kilometers per second per megaparsec, and this difference is becoming more and more statistically significant. This could be either due to some error in calibration, or it could also be due to a lack of our understanding in the cosmological model, which went into the extrapolation of the CMB results from the early universe to the present epoch. So in some sense, cosmology is calling out for new probes, and gravitational waves are a new probe in which standard and via maybe standard science. The next slide is a repeat of what we said just some time back that gravitational waves from compact binaries give us direct access to the luminosity distance, and with the luminosity distance and the redshift, we can obtain all the parameters that go into the luminosity distance redshift relation, essentially the Hubble constant to the first order, then the matter density fraction, the dark energy density fraction, or the dark energy equation of state. But just distance is not going to suffice. We need a redshift. The question is, where can we obtain redshifts from? In electromagnetism, redshifts are very easy to obtain. You see a spectrum, you know that the spectrum is redshifted, you know where a certain spectral line should be, you see it at a different frequency, you divide one by the other, that gives you the 1%. The question now is, are there spectral lines for gravitational wave sources? What do you think?
Do you mean there's a spectrum of gravitational waves?
Are there spectral features in gravitational wave sources? Like in electromagnetic astronomy, you know that a certain transition happens at a certain frequency that gives you maybe a bright line or a dark line, right? The question is there something similar for gravitational waves? We know that there is something that can happen at a certain frequency. Can we read that off and say, oh, it's happening, we see that happening at a different frequency, so it's redshifted by this amount? Yeah, you wanted to add something?
I was saying yes.
Yes. What kinds of features?
From frequency and amplitude, because like when we saw the first figure that you showed us,
Yeah.
where there was a ring down and before the black hole burst, and before there was a steady signal and the amplitude was set.
Yeah. Okay. It's a very good point. So I think you're saying that gravitational wave signals are indeed redshifted. If you start with a certain gravitational wave signal, or if you start with a certain gravitational wave source, if you put it very far away so that there's a cosmological redshift, you put it at a redshift of 2, you observe a frequency that is lower or higher. Frequency is lower. So frequency, if the redshift is 2, then 1 plus z is 3, so the frequency is thrice as low. Okay? So indeed, gravitational wave signals are redshifted, but the thing is we need some kind of the entire gravitational wave signal is redshifted. So we start off with a binary black hole. You start off with a binary black hole signal, which look like something. If you put it very far away, so that there's a cosmological redshift, the whole signal is redshifted to a lower frequency, and this exact effect in the phase would happen if you started with not the same source, but a more massive source with a mass thrice as higher. Once again, using our famous scaling relation. So, just from the gravitational wave signal, at least for binary black holes where there is only gravity, and looking at the phase, it's impossible to say whether the source is at a redshift of 2 or whether the intrinsic masses are thrice as higher. So, for binary black holes, redshift is totally degenerate with the mass of the system. Okay? This is one crucial point. Good. So, however, for binary neutron stars, I think this essentially is coming from the fact that for binary black holes there is only gravity in play. There is no other scale in the system, so this kind of a scaling has to be true. You just can't avoid it. But as soon as you have neutron stars, you break this scaling. Neutron stars have certain features. Neutron stars can have tidal effects, and tidal effects can be tied to certain frequencies. So if you expect, for example, some kind of a resonance in neutron star at a certain frequency, you observe that resonance at a certain other frequency, then you know that this is the redshift at which you are observing the neutron star. Unfortunately, our knowledge of neutron star physics is not yet that good. So we are still struggling to understand the neutron star equation of state. It's difficult for us to use neutron stars currently as these kinds of standard frequency indicators, but maybe in the future, maybe with detectors like the next generation of detectors like the Einstein telescope and the Cosmic Explorer, we will be able to use neutron stars to measure frequencies directly, but unfortunately it's not possible now. There is another effect that is very interesting. Although we do not know although we do not know what kind of masses the black holes are coming from, what kind of masses the black holes have, we know that neutron stars more or less have a certain mass. If one starts observing a neutron star population at a different mass, then one would know how far these signals are coming from. Okay? Because all masses are redshifted, so mass distribution would also be redshifted depending on the cosmology. Once again, we do not know the neutron star masses that well to be able to use this method at the moment. Recently, this idea has been around, the idea of using intrinsic neutron star masses to come up with redshift not for single events but for a population of events. This idea has recently come up again in the context of binary black holes. The question is, do binary black holes have some fixed mass distribution or not? If we know that binary distributions have a certain mass distribution, or if we know that binary black holes cannot have mass above a certain mass, but we start observing binary black holes there, then we know what kind of redshifts these black hole signals are undergoing. So by observing binary black hole populations, one can potentially get some signature of the redshifts. I'm going to come back to this. The clean way of measuring a redshift, however, would be from an electromagnetic counterpart. So if one observes along with gravitational waves some electromagnetic counterpart, which one did for a neutron star, that would give us a very clean, very reasonably sharp measurement of the redshift. So that is our best bet of obtaining the redshift. That's our best bet of obtaining the redshift. I'm going to talk about a redshift coming from galaxy catalogs in absence of counterparts. I'm going to spend quite some time on that. And I'm going to mention some other probes of redshift that can be used together with gravitational wave distance to obtain cosmological parameters. First, bright standard sirens. We already saw that the binary neutron star came with a counterpart, the gravitational wave observation could give us the gravitational wave observation could give us the distance. The electromagnetic counterpart was quickly associated with the host galaxy. The host galaxy, from the host galaxy, we could read off the redshift. We could see the spectral lines in there. With the distance and redshift, we could that's all we needed for cosmology. So we obtained a measurement of the Hubble constant. This is once again the first gravitational wave standard siren measurement of the Hubble constant. This posterior is very, very wide. This posterior distribution is very, very wide. Is that good or is that bad? It's bad. So compared to this is the very sharp CMB measurement. This is the slightly broader supernova measurement. compared to that, our gravitational wave measurement is currently all over the place, which is what you would expect with a single observation. But in some sense, this is the first point in the gravitational wave Hubble diagram. Just like you have the Hubble diagram here, this is the gravitational wave Hubble diagram with just one data point. With about 5% uncertainty coming from the velocity or the redshift measurement, where the dominating error is the peculiar motion of the host galaxy, and about 11% error coming from the distance measurement. So we are dominated by the distance error in this case, giving us a total error of about 14%. Reasonably poor measurement coming from a single observation. Of course, one can do better with more observations. In our case, our measurement precision scales as 1 over square root of n. So we now have a 14% error. What happens if one has multiple events is that one can stack up. These are also individual posterior distributions coming from different events. If one stacks up the result from individual events, one can get a sharper, so a better joint estimate. The scaling I mentioned goes as 1 over square root of n. Currently, we have a 14% uncertainty. If we want to go to 1% uncertainty, how many similar measurements do we need? Yeah?
You mean 100% certainty? You need infinite number.
No, not with 100% certainty. What I'm saying is, our measurement uncertainty now with one single observation is 14%. Okay? The error in the measurement is 14%. If we want a 1% error, then how many detections would we need? Our uncertainty scale with the number of detections is 1 over square root of n.
100.
And 100 is? Square of 14. So it's about the square of 14, whatever it is, and that is the order of 100. Yeah. Yeah, it's actually 200. Yeah. Okay. Okay. And how many do we have? 1. We still have 1. Okay. So the one important dimension that the distance measurement is the distance uncertainty is the dominating uncertainty. A large part of this distance uncertainty once again comes from the degeneracy between distance and inclination. So here, what you see is a plot, not a one-dimensional plot of the Hubble constant, not a one-dimensional posterior density of the Hubble constant, but a two-dimensional posterior density of the Hubble constant on the horizontal axis and the inclination, or rather the cosine of inclination on the vertical axis. What has been done in the previous plot is one took this two-dimensional posterior distribution and kind of squeezed it like this, flat, and one obtained the projection. However, if you do not squeeze it, if you slice it, okay, if you slice it, then you would obtain a much better estimate of the Hubble constant. And when will you be able to slice it? You would be able to slice it if you know the inclination well. So if somehow you know the inclination well, then you don't need to essentially marginalize over all these values of the Hubble constant. You can take a slice through it, which would look much sharper. And this was already done by a separate inclination measurement coming from the jet. So if you trust the jet models that went in, then you could already improve the Hubble constant measurement by quite a huge factor over here. The inclination measurement can also come separately from gravitational wave observations alone via what are known as higher modes. Almost all the expressions that I gave you was about the leading order gravitational mode. What's the leading order gravitational mode? The leading order gravitational mode would be like the lowest harmonic of the spherical tensor harmonics. It's not a very accurate plot, but if instead of the lowest harmonic, you could observe also the next harmonic would have a different angular dependence. Essentially, every harmonic would have different angular dependencies. This is like doing an expansion in spherical harmonics, which you are familiar with. The only thing is these are not the usual spherical harmonics, but tensor spherical harmonics. So if you really are able to observe the higher mode waveforms, then the higher modes different higher modes would have slightly different angular dependencies, and that can tell you the inclination better. And if you are able to measure different polarizations, then different polarizations would also be able to tell you the inclination better. So having multiple detectors would also help break this distance inclination degeneracy in the future. Now, higher modes was something that we were not really expecting to observe, but already with some of the more asymmetric signals, we have started observing higher modes in gravitational waveforms. So, there is probably merit in trying to think about how higher modes can already help break this distance inclination degeneracy and give us slightly better results. Okay, all of this was in context with counterparts. But as you answered already, of all these 90 events which we have observed so far, only one of them, the one over here, only one of them has a counterpart. I think this is the one, sorry, this was not GW170817, this was it. So only that event has a counterpart, the others do not have a counterpart. Can we do any kind of standard side cosmology with all these other events that do not have counterparts? The answer is yes, we can. And one way to do it would, of course, be to use the mass distributions and see how the mass and see whether we have an expected mass distribution which changes with redshift. Unfortunately, we do not have a very expected mass distribution for all these binary black holes. However, some people here, they have shown that if there is a feature like a sharp cutoff in the mass distribution, which you expect from something called the pair instability supernova process, which should not give rise to black holes higher than 40 solar masses or 50 solar masses maybe. If there's a sharp cutoff in the mass distribution, then that sharp cutoff is going to show itself in then how the sharp cutoff affects the observed mass distribution would depend on the cosmological parameters. So from the observed mass distribution, assuming that there is a sharp cutoff, one can estimate cosmological parameters, and these people have also shown that it does not really matter where exactly you have this PISN cutoff. It could be at 40, it could be at 50, it could be at 60, as long as it is there, and as long as the feature is there and is reasonably robust. Of course, these are qualitative statements, we need to quantify them better. They show that one would be able to measure redshift by using the mass distribution. It's a poor measurement, but it is a measurement. The other way that redshift can come in is statistically from galaxy catalogs, and how this exactly works I'm going to illustrate with a kind of a cartoon animation which I have here. This idea dates back to 1986 from Bernard Schutz, the same paper, the same phenomenal paper, which told us first that compact binaries were indeed standard sirens. So let's walk through this cartoon. Let us assume that we have a distance estimate coming from a gravitational wave source, and let's say a very sharp Z value, a very sharp redshift value coming from a counterpart or an identified host galaxy. If one takes this distance estimate and this value of the redshift, convolves them together, one obtains an estimate on the Hubble constant, a very nice unimodal estimate, as we saw for GW 1708-17. Okay? However, I just said that one is often not able to identify the host galaxy because there is no counterpart, so there is no unique host galaxy. Instead, what one has done is one knows more or less which area of the sky this gravitational wave source has come from. One has looked at all the galaxies in that, giving some reasonable priors on H0, and one has identified certain redshift values from all the different possible galaxies. So instead of one sharp redshift, one now has 5 different redshifts in the cartoon animation. What would happen if one takes these 5 different redshift values and convolves that with the distance estimate? One would obtain not a unimodal H0, but a multimodal estimate, and some of the peaks might fuse together, as it is in this case. These two galaxies, these two Z values are close together, these two Z values are close together, they fuse into one peak each, they also somewhat fuse, so one obtains a distribution of 3 peaks over here. This distribution with 3 peaks is not informative at all, right? You do not know which is the correct peak, which is the incorrect peak. You cannot do much with this. However, consider now a different gravitational wave detection. A different gravitational wave detection in a different part of the sky, which came with its own distance estimate, a totally different distance estimate, a totally different set of possible galaxies in that sky area. That would give a Hubble constant estimate, also multimodal. Here we see 4 peaks. Once again, we do not know which is the correct peak, so this distribution by itself is also not useful. Now consider not one or the other, but many such detections. So, not one, not 2, but many such detections. A crucial thing that essentially Schutz noted was, of all these peaks that you see, one of them, for all of these different detections, one of them would be the right peak at the right location. And all the other peaks, which are due to incorrect associations, they're at random locations. So if you stack up information from many different observations, then the peak at the right location, which is always there, would get enhanced, while the peaks at the random locations, which are at random locations, they would get suppressed. So if one combines information from multiple detections, in spite of the individual posterior distributions being multimodal, one is driven to a joint unimodal distribution, demonstrating the power of statistics in the method. So, can one do slightly better than the cartoon I talked about? Can you think of any way, any obvious way in which we can do better than the cartoon we talk about? In the cartoon, we assume that all these galaxies, or from all these galaxies, they have equal weights. All these peaks, these delta function-like peaks, they all have equal heights. One can give more weight to some of the galaxies than to the other galaxies. Okay, so what one can do is one can assume that the brighter galaxies are more likely hosts, so one can take the brightness in a certain band, like one can take the brightness in the B band, which is a proxy of the star formation rate. One can take the brightness in the K band, which is a proxy for the total mass. This is also an assumption what band is best at the moment, and one weights the galaxies according to their luminosities, assuming brighter galaxies are more likely hosts. This already improves the efficiency of the method by a factor of about 1.3. Okay, you have a question?
Yes, but this somehow biases the result, right?
It may bias the, okay. It biases the result with respect to what? If you, if you say that it biases the result with respect to putting equal weights to all galaxies, then I'm going to object to that, because I can claim that maybe giving equal weight to all galaxies gives a lot more weight to fainter galaxies and biases the result. So I think at a bare basic level, using some kind of a luminosity as a proxy for gravitational wave events is reasonable. What is the correct luminosity to weight? We do not know yet. And if we have enough number of events, then B band and K band luminosities, weighting by B band and K band luminosities can give different results. And one of them would be correct, one of them would be incorrect, depending on essentially the population scenario of gravitational waves, whether gravitational waves are more correlated with the star formation rate, or whether gravitational waves are more correlated with the total mass. Okay, so you are absolutely correct in saying that choosing an incorrect band may lead to a bias. Okay, but it is probably still better than not giving any weight at all. I will also comment on this on the current results. So this is actually a very important point. Okay, so you also start seeing this. Start seeing about the interplay between gravitational wave astronomy and conventional astronomy. And I mean, these are the kinds of things that, for example, I myself would not have the expertise in, but I would like to work with people like people who are experts in astrophysical population simulations or astronomy observations. People like Maciek, who you heard from yesterday, and to improve this kind of a measurement and to reduce potential biases in such statistical methods. Okay. Of course, the full story is complicated. The thing is, we already saw that some of the peaks were fused together. One is not really seeing things event by event. However, the information is already there, even if multiple peaks are fused into one. One thing to highlight here is that we are essentially tracing the underlying matter distribution. There is an underlying matter distribution or underlying dark matter distribution which is somehow correlated with the gravitational wave distribution. How exactly it is correlated, we do not know. Maybe it's correlated by something called a gravitational wave bias. So that is what we are also we would be trying to measure. And some astrophysical models would also go in, how to take the underlying matter distribution and convolve it into a gravitational wave source frequency distribution in redshift space. There is Third effect that I wanted to mention, which is the contribution from beyond line of sight, which is essentially would come from cross correlations. So you can think about, you know about the large scale structure in the universe, you're a cosmologist. So you can think about trying to map out the large scale structure in the usual redshift space versus the large scale structure in the distance space which we are observing in gravitational waves. Now, if one takes the large scale structure in the redshift space and the large scale structure in the distance space, then they are essentially related by cosmological parameters. If one takes incorrect cosmological parameters and looks at some ring in the sky, incorrect cosmological parameters, and take some shell in the sky, and then the shell in the distance space and the shell in the redshift space, they would not, they would show a low correlation with each other, right? It would be a random. You'd be seeing noise. However, as you change the cosmological parameters, at the right value of the cosmological parameters, the structure in the distance space and the structure in the redshift space, the structure in the distance space coming from the gravitational wave observations, the structure in the redshift space coming from the distance observation, from the electromagnetic observations, they would show a sharp match. So otherwise there's, you see random things, otherwise you see random things at the correct value of the cosmological parameters, you kind of see a match. So essentially the large scale structure of matter, it acts as some kind of a fingerprint, and it, for example, you know that the matter power spectral density peaks. There's a peak at a certain scale. If the peak in the distance scale matches with the peak in the redshift scale, then you have the right value of the cosmological parameters. So this way, beyond line of sight contributions can also give you a distance estimate. Unfortunately, our gravitational wave detectors, as I said earlier, have very poor angular resolution. So at least with the current generation of gravitational wave detectors, this is not a very promising avenue, but maybe with next generation of gravitational wave detectors, just the spatial location of all the gravitational wave events can tell us about cosmology. Okay. It's about 5:30. I will have to see how much I talk about and how much I skip. Selection effects is okay. Let me pause and ask. Let me stop and ask if there are any questions. And in the meantime, in the background, I'll think about, as you can see, I have a number of slides. I don't want to cover the whole of it. In the meantime, I'll think about what I want to cover in the remaining half an hour or so, and what I can skip. Yeah.
So I just wanted to have this understanding clear about what you just said. So you are taking these at different redshifts. I mean, those, I think they're cosmic web structures, right?
Yeah, this is the cosmic web.
Yeah, so they're at, I think, Z is equal to 0.0026, and then at different, then you're cross-correlating them, and then you're seeing the, like, the peak is for the gravitational wave. The peak is the part which cross-correlates the best.
Yeah. That peak is the part that cross-correlates the best, and you will see the best cross-correlation only if you have the right cosmological parameters, right? Because you're trying to correlate something in the redshift space with something in the distance space, and they are related by unknown cosmological parameters.
Yeah, I wanted to ask one thing. Like you said, if I have the value of, let's say, the Hubble parameter or let's say cosmology parameter, so the gravitational wave signals which I am detecting, if I detect, let's say, 100 or 200 detections, then not those detections, but the L is equals to 3 mode in that detection will help you better constrain the H0, or only L equal to 2 will suffice? Or I need L equal to 2 and L equal to 3 modes in my gravitational detections.
Oh, you were talking about the higher modes of gravitational waves. Like for first time I thought you were talking about. Okay, very good question. Important topic, yeah?
Yes, so I mean, so if I have 50 detections more, so in order to constrain Hubble constant or cosmology more effectively, not only on I need detections, I need L equal to 3 mode also, right? Or if I just get L equal to 2 modes and it would be fine.
No, so the thing is, what I was trying to emphasize here is for a single detection, if in addition to L equal to 2 mode, you are also able to observe L equal to 3 mode. Okay, the thing is, in the detector strain, you would already see a sum of L equal to 2 modes and L equal to 3 modes. From the detector strain, you cannot say that I don't want to see the L equal to 3 mode. You would be able to detect the L equal to 3 mode if the system is asymmetric, if one of the masses is much bigger than the other mass, in which case for asymmetric systems the higher modes are automatically higher if the system is asymmetric. 2, if the detectors are more sensitive, then you'd be able to make out the L equal to 3 mode. And with multiple detectors, you may be able to make out the L equal to 3 mode better, because if you have multiple detectors all over the earth, then multiple detectors are pointing in different directions. So you're observing things from different angles, and if you're observing from different angles, then the L equal to 2 mode and the L equal to 3 mode, they behave differently. Okay? The L equal to 2 mode and the L equal to 2 mode, they affect the different polarizations differently. So you would see, you would make out that from the polarizations you can see how much of L equal to 3 mode is there. Yeah.
Can we? Because maybe not. Right. I will ask it personally.
You'll ask personally later, that's also fine. Yeah.
Yes, so I want to ask about when you were talking about the bias which is there for the weight and luminosity relations of the galaxy. Like the weight and luminosity relations, there's a bias that we put.
Yeah.
Yes, so I just wanted to ask if there are any observational constraints on these biases. Like for example, like do we take this, assumption randomly, or is it more observational evidence that we take?
No, are you talking about, let me just make sure, you're talking about something on this slide? Okay, the same question about beam, or whether which band we should use. Okay. Yeah, so the thing is, with of the order of 100 observations we have now, it is difficult for us to say whether the gravitational wave sources are more correlated with star formation rate, or more correlated with the stellar mass. If you observe many more observations, you know how the star formation rate behaves with redshift, and you know how the stellar mass evolves with redshift, right? And they have different evolutions. So if you have more observations, then looking at the mass distribution as a function of redshift, you would be able to say whether our gravitational wave sources are more correlated with star formation rate or with the stellar mass.
Understood.
Yeah.
I have another question. So when we do distance measurements using electromagnetic counterparts in gravitational wave studies, we are assuming the cosmological background, right?
We are assuming the cosmology?
Yes, because in the distance from luminosity relation we consider the omega?
So it depends on what you are interested in doing, right? Okay. First of all, if you the distance measurement is independent of cosmology. The distance measurement is direct.
But in the luminosity distance relation, we have the xt, and that is, we are considering the equation like hz by h naught equals omega m and 1 plus f2 plus.
Yeah.
So we are assuming the cosmological background in this context, right?
No. This is the relationship between distance and redshift. This is a generic theoretical relationship, right, between distance and redshift. But our gravitational wave amplitude over here. So it's a simplified expression, the complicated expression you saw in the previous lecture, that has this redshifted mass on the top and just the distance in the denominator with nothing else. So we are really directly measuring the distance. There's no redshift anywhere other than within the mass.
But in the next slide, when we are having that h naught and that thing, this thing, so that h naught comes from, I guess, a dot by or something. That is FLRW dependent, right? That is metric dependent.
Yeah. So that is
different.
That is there in the cosmology, right? On the theoretical side, of course, distance depends on redshift, right? Distance depends on redshift. If you're usually thinking about some measurements, then what you have in the back of our what we usually have in the back of our heads is a measurement coming from the electromagnetic sector. We think of reading of redshifts of different sources. Okay, for a gravitational wave measurement, at least with compact binaries, we do not really measure the redshift of the source. Okay.
But in the electromagnetic counterpart, we are measuring DL.
No, with the electromagnetic counterpart we measure the DL, but from the gravitational measurement, from the gravitational wave measurement, we did not measure the DL. From the gravitational wave measurement, we measured, from the I switched it around. From the electromagnetic counterpart, we read out the redshift, but from the gravitational waves, we could infer the distance, just the distance directly. From the amplitude. Yeah.
So the 70 plus minus we have value from the 17,017, it's using this relation, right?
It's using this relation. The thing is, that particular detection is so close that you don't really need to go beyond the linear lemma Hubble law.
But now, like it was like a redundancy, like it is coming back to lambda, like the trials. That was my question.
This is see, you can think of a luminosity distance measurement independent of the lambda CDM model, right? Luminosity distance is an independent quantity which tells you how much if you place a source at a certain distance away, you would expect a certain luminosity. You see the luminosity falling off, and from that you infer the distance. That's the luminosity distance, and that is quite independent of the lambda CDM model, right?
Is the luminosity, the distance modulation?
The luminosity?
The distance modulus relation, you mean by that?
The distance modulus relation does not depend on the lambda CDM model, right?
Yes. Yes, I'm asking, you mean that relation?
Yeah, exactly.
Okay,
yeah, I mean, okay, here we don't talk about the distance modulus because the distance modulus usually is used in conjunction with magnitudes and
so if I may add, I mean, the truth is that this luminosity distance does not come out from the definition of how the flux scales with the distance, but from the particular, fine arrangements in the calculations that if you take into account that frequency gets redshifted,
Yeah.
in the calculation everything restores, the non-cosmological decays. Whenever you identify the chirp mass with the redshifted mass, there is no other sense to, introduce the redshifted mass. But this is the one which is observable, and when you identify the measured distance with the luminosity distance. Because the truth is that the amplitude should scale like a comoving distance, but this z, 1 plus z factors are manipulated in the equations in particular such a way that what is measured is the luminosity distance. And as we heard from the lectures, these seminal works by Bernard Schutz, but highlighting the Polish pride, Bernard Schutz and Andrzej Królak, another paper that appeared. Yeah, sure, Bernard Schutz 86 was the first, but the year thereafter we published with Andrzej Królak on the same topic. It was incredible that standard sirens, in spiraling, again stressed, you perhaps taken it from this lecture, but this particular class of sources, no other class, no exploding supernovae, no, any other, just chirping binaries are so exceptional that from the strain, the amplitude, combined with how frequency evolves, with time, one is able to extract two things, mass and distance. And at cosmological distances, it turns out that this mass is not the rest mass, intrinsic mass, but the redshifted mass, and the distance is not the comoving distance, but the luminosity distance. So this is the truth. And so we have a weird situation that we are plenty of sources. What we measure, we know that this is a measure of luminosity distance, not necessary to calibrate to attach to any distance ladders or whatsoever. It is a pure measurement of distance. So this is a huge advantage. Leaving aside all this, the precisions of inference and so on. So this is extremely fascinating. Yeah, but now, there is nothing, no such thing like a free lunch, so in most cases we have problems with redshift, so we must be smart about that. So this was the...
Yeah, indeed. Okay. So in the meantime, I decided that I won't talk about selection effects, which are our primary source of, which essentially are our primary source of potential systematic errors at the moment, because the selection effects, they depend on the population of the gravitational wave sources. The summary is that the selection effect depends on the population of gravitational wave sources, which is itself not known. And so what one has to do is one has to measure the population together with the galaxy catalog. This also brings the previous slide where I was talking about measuring features in population, using features in population to measure cosmology. Essentially, before one measures features in population, one has to know the features, and the features are not known. So what one should do is one should simultaneously measure the population parameters, which would include all these features in population together with the cosmological parameters. And essentially, that's the direction that we are moving towards. We are trying to move towards computing H0 and population parameters simultaneously. Okay, this was the summary of selection effects. I already said in words, said out aloud what is written over here, whatever is needed for selection effects depends on source population parameters, so one has to do a joint estimation. With galaxy catalogs, there's also another effect that the galaxy catalogs are not complete, so one has to model the out of catalog term, which we are also currently doing, otherwise one would be led to a bias. And we have some results putting most of this in. We are not doing a very rigorous job at the moment. For example, we are not doing a simultaneous estimation, we are doing an estimation in 2 steps. This is essentially just from the population. This is at the first stage we estimate just the population, then we take the population and estimate the cosmological parameters, then we vary the population slightly to check if our results are robust against changes in the population parameters, and currently the results are robust. We check our so this is the current LIGO-Virgo measurement coming from this was the GW17 0817 measurement, the black line. If you add to it the population features, you get with just the population features, you would have gotten the results from the previous slide. With just population features, if you add in contribution from galaxy catalogs, then we would be improving the measurement by about this much. So we do improve the measurement already with the galaxy catalogs. Of course, we are trying to attempt a precision measurement. We should be very, very careful about all kinds of systematic effects, and these are some of the systematic effects that we need to be careful of. A list of systematic effects are peculiar velocity flows, various uncertainties that are coming from the galaxy catalog sector for the EM measurement, especially using galaxy catalogs, redshift uncertainties, estimates of luminosities, effects on the gravitational wave side, population properties, which is very important for selection effects. Many things there are unknown. Now, the more important effects on the gravitational wave side are currently subdominant. These are gravitational waveform uncertainties, and the gravitational wave detector calibration uncertainties, which are eventually going to dominate our result. But we know that they are much smaller than 4%, while our distance measurement is of the order of 10%. So these are currently not very important. Once again, they are going to become important as we are moving towards a precision measurement. As I said, we are always thinking about various different systematic effects, and this probably answers the other part of your question. So whenever we were doing this measurement, we try to make sure that if we choose different bands, we do get results that agree with each other. As soon as results from different bands will start disagreeing with each other, we would not know which is the right band to use, and we would need something that's more physically motivated, more astrophysically motivated to trust one result over the other. We are trying to quantify the effect of redshift and luminosity uncertainties. Actually, this work is being led by Cesare, whom some of you here may know. Okay, so of course, we are limited by the number of sources. We can try to, especially for counterparts, we do not know how many sources with counterparts we are going to see. Possibly rapid EM follow-up, possibly early warning. There's a possibility the signal from a neutron star is really long. It lasts about 2 or 3 minutes. If one can observe the very early bits of the inspiral of the neutron star and send out an alert right away, then it increases the chances of observing the counterpart, okay, at least a little bit. With galaxy catalogs, there's of course more prospect. One can go for deeper surveys for galaxy catalogs. There's also the possibility of following up that patch of the sky later. If one observes a very well localized event at a certain distance, one can follow that patch up later to observe all the galaxies and get deep redshift information from a certain part of the source. And that will certainly lead to an improvement. I talked about systematic effects already. So, who knows? This was the improvement with galaxy catalogs of the order of 10 detections. This is the improvement of the order of 90 detections. And who knows? Maybe we will be able to shed light on the Hubble tension 6 or 8 years from now. Okay, I already mentioned some of the future detectors which are planned. You saw it in the previous slide. So the future generation of ground-based detectors, this is the sensitivity of the current advanced LIGO instruments, the proposed Einstein telescope and the Cosmic Explorer are going to be more than an order of magnitude more sensitive, and one is going to observe. This is this is as a function of total mass in the source frame, how far we can observe such objects, and as you can see, we can observe some 10, 20, 30 solar masses to up to a redshift of 100. We do not even know that such sources are there up to such redshift, so probably not. So essentially what we'll be observing is, the stellar mass black holes, all stellar mass black holes that can be there. And for example, if there are some lower mass black holes which are seeds of supermassive black holes, some 100,000 solar mass black holes which are seeds of supermassive black holes in this era, we would be able to observe them using these third generation of gravitational wave detectors. I mean, by that time the current tensions in cosmology may have been resolved, but the standard sirens are still going to remain a direct probe of the luminosity distance, and we are going to measure distance directly, not here, but at whatever redshift we are observing. So one can probe not just the cosmological parameters, other cosmological parameters such as omega matter, W naught, but also maybe parameters beyond lambda CDM. The next two slides are some of the other prospects. I'll skip these for now. I'll briefly mention the space-based detector concept, LISA, which is going to measure, essentially this is a concept of the LISA. It is a triangular configuration that's going to follow the Earth around its orbit, and the LISA is going to be sensitive to different sources such as these not only stellar mass binary black hole, but also supermassive black hole binaries, and some of these LISA supermassive black hole binaries are going to have electromagnetic counterparts as well. Okay, so this is a quick summary of the future of standard siren cosmology. I already showed this slide in the previous lecture. What I'm going to highlight is that with LISA, there's also the prospect of doing multi-band gravitational wave astronomy. So it is possible that you can see a certain source in LISA, the very early inspiral of a source in LISA, and maybe a year or 10 years later, the source leaves LISA and a year or 10 years later enters the LIGO-Virgo band. So if you already saw the source in LISA, you could predict that this source is you are going to see in the LIGO-Virgo band a year from now or 10 years from now, and then you see the merger. Or it could be that you see something in the LIGO-Virgo band, and then you look up LISA data before that, and you actually observe it in a much low frequency in spiral regime, and then you can test various things such as how the signal has been evolving all this time. Is that consistent with general relativity? Is that consistent with the cosmological model? I mentioned other different sources in the previous lecture, and particularly the stochastic gravitational wave background is another very important aspect of how gravitational waves are connected to cosmology. Unfortunately, I'm not talking about that, partly because that's not really my field of expertise, but essentially I already mentioned briefly that the frequencies spectrum is different from for astrophysical and cosmological background. So once one observes this once one observes this stochastic background, one would be able to make out, whether it's an astrophysical background or a cosmological background. There can be certain cosmological models which can give an a large amount of stochastic gravitational waves even with the current generation detectors. So we are already putting constraints on various models such as cosmic strings and phase transitions from the current detection. So we'll definitely put stronger bounds or maybe detect some of these exotic systems. And finally, just like we do with the CMB, with the angular dependence, we will be able to probe the large-scale structure, of course with the caveat that our angular resolution is intrinsically poor. Okay, so hopefully I could convey the message that standard sirens are really cool. They give us a direct estimate of the distance, which was also highlighted by Mark. It's really fascinating. You can measure distance directly without any kind of calibration, any other kind of calibration. Maybe it will shed light on the Hubble tension. Maybe it will probe the redshift dependent Hubble factor. Of course, there are lots of caveats which we are working hard trying to address, and perhaps gravitational waves are going to become a standard probe in cosmology in the decades to come. So this is only the beginning of gravitational wave astronomy, right? I mean, almost the whole of astronomy and physics, we know astronomy and cosmology depends on electromagnetic observations. And here you see Galileo with one of the he was not the inventor of the telescope, but he definitely popularized the telescope. So you see Galileo with his telescope. So and that led the birth to modern astronomy. And now it's we have just invented an analog of Galileo's telescope in gravitational waves. We are yet to discover what is lying in different bands and also in the same band of gravitational wave astronomy. Okay? With this note, I'm going to thank you for your attention.